Okay, so in this lesson we're going to cover types of reactions. So there's 5 major types of reactions that we're going to go over today, and the structure of all these slides is going to be the same. We're going to give you the reaction type, and then this first line here is going to be the gist of the reaction, the main point of what it is and what it does. Then we're going to have the general form here and a real example. So the first type we're going to go over is synthesis. So synthesis is combining, it's a combination. So if we look at this general form here, what we have is two separate things, let's say A and B, combining into one thing. So A plus B separately makes AB as a new compound that's a combination of the two. This is the major form of synthesis reaction that you're going to be seeing, two things combining into one thing. This form down here, it's another type of synthesis. We have in this case C combining with A and B separately. So C goes with B and makes BC. C also goes with A and makes AC. So it combines with A and B separately. This isn't as common. You'll see on the Regents much more of the A plus B making AB type direct combination reaction. So a real example of this is the Haber process. This is a process we use to make ammonia. It's really common because ammonia is used a lot in the industrial setting. Ammonia is used to make fertilizer. It's also used to make explosives. So if we look at this, we have nitrogen and hydrogen combining to make NH3. So originally the nitrogen and the hydrogen are separate, and then we combine them because synthesis is a combination. We combine them to make NH3. So what you need to know about synthesis is that it's a combination. We're taking two things, combining into one. So the next type of reaction we're going to go over is kind of the opposite of synthesis. It's decomposition. So you probably know decompose means to break down. So a decomposition is something breaking up into parts. So the general form is the exact opposite of synthesis. We have one thing, AB, breaking up into two things, A plus B, separately. So we start with one compound and we end up with the parts, A and B. So an example of this would be KCl, one ionic compound here, breaking up into its parts, potassium and chlorine. So again, decomposition is breaking up, so we're breaking KCl into K and Cl. So we can compare synthesis and decomposition, more accurately contrast them as opposites, because synthesis is two things becoming one and decomposition is one thing becoming two. So synthesis and decomposition are opposites. That's very important. If we take a synthesis reaction and essentially reverse it, so if we went this way instead, we would have NH3 becoming H2 and N2. We'd be breaking the NH3 up into its parts. So if we're breaking up into parts, that would then be a decomposition reaction. If we take the decomposition reaction and go the other way, we have two parts going into one part, merging, kind of mashing together. That would make a synthesis reaction because it's combination. So synthesis and decomposition are direct opposites of each other. So it's best to really think of them together, and then because you're going to have to memorize these 5 types of reactions. So if you think of synthesis and decomposition together, that can help you kind of remember what they each do. So the next type of reaction we're going to go over is single replacement. So single replacement is a substitution. So what that means is we're taking a lone element here. Let's look at this general form example, and we say C is going to substitute in here for A. So we have then, instead of AB, we have CB. So C has come in and kind of just kicked A off here, and A goes off on its own. So C substitutes in for A. Single replacement is a substitution. So in this case, remember, the cation comes first, so A would be a cation here, and B would be an anion. In this case, we have C coming in and substituting for A, which means C must be a metal, because metals form positive ions. It doesn't necessarily have to be a metal, but C, we could say, is something that is going to form a positive ion, most likely. So C comes in, kicks off A, and C becomes the cation then, and B is still the anion. A goes off on its own. So this is the most common form of single replacement that you're going to see, is the cations replacing. It's also possible to have an anion come in and replace the anion in the compound. So in this case we would have C coming in for B, substituting in and kicking B off, and that would give us AC plus B. So again, it's much more common to see cation switching, but it is possible to have anions come in and substitute as well. But either way, it's a single replacement. We're only substituting one part of this equation. So for a real example, we have zinc and copper chloride making zinc chloride and copper on its own. So if we look really with these reactions, to distinguish them, you want to look from left to right and see what happened. So we had copper chloride, now we have zinc chloride. So what must have happened is that zinc came in here and substituted in for copper and then kicked off the copper. So that gave us zinc chloride. Zinc is now with the chloride because it's coming substituted in here, and then the copper goes off on its own. So single replacement is just one substitution. By contrast, double replacement is two. Double means two, so double would be two substitutions. This would then be an exchange, or you could think of it as a trade. So AB plus CD makes CB plus AD. So what happened here? Well, C and A switched with each other. So basically C subs in for A and A subs in for C. So it's a mutual exchange. So instead of just having one thing come in and substitute, we have two things mutually switching. So again, we're going to switch cations with cations. So we're going to switch the cations here. C is going to come in for A and make CB, and A is going to come in for D and make AD. So we're switching the cations here, and for a real example here we have sodium chloride and calcium fluoride making calcium chloride and sodium fluoride. So what we did here, the sodium was originally with the chlorine, so we're going to switch the cations, and now the calcium is going to come in here and be with the chloride, and that's how we end up with this. And the sodium is going to come in here and end up with the fluorine, so we end up with sodium fluoride. So we're switching the cations. That's the key here with double replacement. So it's really best to try and think of single and double replacement together because they can kind of be compared. So we have synthesis and decomposition that we're going to put together, and now we're going to put single and double replacement together. So single replacement is a substitution, a single substitution. So we're just doing one substitution. Double replacement is an exchange or a trade. It's a mutual replacement, two replacements. So here we have zinc, a lone element. It comes in here, subs in for the chlorine, the copper. The copper gets kicked off, and we end up with zinc chloride. That's just one single replacement. The zinc replaces, and we're done. The double replacement, though, is a mutual replacement. We're replacing twice. The sodium replaces the calcium, and the calcium replaces the sodium. They switch, so we have two replacements essentially. So you want to be able to keep double and single replacements straight. Again, you can just kind of think, how many replacements did we do? In this case we did one, in this case we did two. So two double, one single. So the last type of reaction we're going to talk about is combustion. So what combustion is burning. You've probably heard of the word combustion before. It means burning. So the general form, this is really important here, the general form, I'm going to highlight this in a different color because it's very important. You need to memorize this general form for combustion. It's hydrocarbon plus oxygen makes carbon dioxide and water. So it's very important here. This could be something else besides a hydrocarbon. Like really it could be, we could just call this something. Anything plus oxygen makes carbon dioxide and water. The most common form of combustion you're going to see on the Regents exam and in the rest of your chemistry course is going to be hydrocarbon plus oxygen making carbon dioxide and water. So to help you remember this, you can think of your car. We all know that cars spit out carbon dioxide basically, and that's why global warming, right? Greenhouse gases, carbon dioxide is one of those greenhouse gases, and that's why cars contribute to global warming. So if carbon dioxide is a product, we know it's a product of our car, we know it's got to be a product of this reaction because in our car we burn gasoline. So the other way you could think of this is for the oxygen part, we could think of a candle. So a candle, if we, let's say, put a candle in a big jar and then we cap that jar, what would happen is the candle would eventually go out. And the reason for that is when we cap the jar, we're limiting the amount of oxygen that this candle has. When we seal the jar, we're depriving it of oxygen. It has the oxygen that's left in this jar, but nothing else. So once it runs out of oxygen, for the candle to burn, it needs this oxygen. This oxygen is the fuel of this reaction. So if we keep burning this candle inside the sealed jar, it's going to eventually use up all the oxygen in there. Once it uses up all the oxygen, it can't burn anymore. Oxygen is a necessary component of this combustion reaction. So it runs out of oxygen and it can't go anymore, so that's why the candles go out when you cap the jar. So we can think of oxygen as a reactant here because it's something that we need to make the burning happen. So we have hydrocarbon plus oxygen makes carbon dioxide and water. That's really important to memorize this form. And then down here we have a real example of the equation for actually burning gasoline. Gasoline is mostly made of octane. So octane here, if we add octane to oxygen, we get carbon dioxide and water as long as we're burning there. To really start the burning process, if you just put gasoline next to air, which has oxygen, it's not just going to burn. You need some sort of energy source or spark to make that happen. But realistically, the format you need to know here, hydrocarbon plus oxygen makes carbon dioxide and water, and it's going to be the same for any combustion reaction. So let's take a look at a couple of examples here and decide what type of equation we have. So basically at the beginning of each of these examples, I'm going to pause for a second, and you can pause the video if you want, think on your own, and see what type of reaction you think this might be based on what we've discussed so far. So take a second and try and think about this one. You can pause the video if you want. I'm going to go ahead and give the answer. This is a decomposition reaction because we're breaking up. So we're breaking up the water here into two parts, the hydrogen and the oxygen. We're breaking up. That's a decomposition reaction. Again, I'm hoping that you took notes at the beginning of the video when we talked about these different reaction types, but because this is a breaking up, that's a decomposition reaction. So the next example here, we have lead chloride and lithium sulfate making lead sulfate and lithium chloride. So again, pause the video if you want to try and do this on your own, but the answer here is going to be double replacement. So why is that? Well, double replacement we said is an exchange. So if we look at the left side here and the right side, what happened was we switched the cations. We started with lead with the chlorine, and now lead is with the sulfate, so it came over here and joined with the sulfate. The lithium was originally with the sulfate, now it's with the chlorine, so we switch. This is an exchange. So an exchange means double replacement. We replaced twice here, 2 for double replacement. Alright, the next example we have here is C6H14. This would be hexane, but we'll talk more about those organic molecules later in the year. And then we have oxygen making carbon dioxide and water. So here what this is combustion. So combustion looks different than the other forms we have. With single and double replacement, we have some sort of switching. There's no switching going on here. We don't like switch the oxygen in for the hydrogen because the oxygen also goes with the hydrogen. We could also think, is this a synthesis or a decomposition? We're not really merging the hydrogen or the hydrocarbon and the oxygen together. We're not merging them together in this new form. We're not breaking them apart. They're already broken apart. So this isn't really going to be decomposition or synthesis either. It's going to be combustion. Again, this follows the general form of combustion, which is something plus oxygen makes carbon dioxide and water. So you can kind of distinguish the combustion reaction because it looks different than the other ones. There's no switching involved, so it's not a replacement. There's no breaking up, there's no merging or combining, so it's not going to be synthesis or decomposition either. So the next example we have here, potassium chloride plus calcium makes calcium chloride plus potassium. So pause the video if you'd like to try this, but the answer is going to be single replacement. So why that is, we have one replacement here. Calcium comes in for the potassium, kicks it off, and we end up with calcium chloride. So this is a substitution. The calcium substitutes in for the potassium gets kicked off, and we end up with calcium chloride and potassium by itself. So because it's just a single substitution, that's going to be single replacement. So the next example we have here, silver nitrate plus sodium chloride makes silver chloride and sodium nitrate. So again, pause the video if you'd like to try this, but the answer is going to be double replacement. So again here, double replacement is a mutual exchange, a trade. We have two replacements here. The sodium comes in for the silver and pairs with the nitrate, and we end up with this. The silver comes in with the chloride and makes silver chloride, and we end up with that. So again, two replacements here makes double replacement. So another example here, we have mercury oxide making mercury and oxygen. So pause the video if you'd like to try this. The answer is going to be decomposition. So decomposition, we said, is going to be something breaking up. So this is pretty clear here that we have one compound breaking up into two. We have the mercury oxide breaking up into its parts. Mercury and oxygen breaking up is going to be decomposition. That should be pretty straightforward by this point. Our last example here is C3H8 and oxygen making carbon dioxide and water. So this should look familiar. This is the same format as before. Pause the video if you'd like to try this on your own and think for a minute, but this is going to be combustion. This is the general form we have for combustion. Hydrocarbon plus oxygen makes carbon dioxide and water. So we have the four parts of combustion here. There's no replacing, there's no breaking up, there's no combining. This is going to be a combustion reaction. So this is all we're going to do for today. If you are still struggling with these reaction types, go back to the beginning of the video and take some more notes and try and understand a little better. Listen to the explanations again about what each of these types of reactions mean. That's all for today. I'll see you in the next video. Thank you.